or here, because there is no differentiation between these two carbons. They are absolutely identical as far as sterics and electrons. Now, if we follow our example and we put a methyl group here, again, the same reaction with bromine. We form again bromonium ion. In fact, what I should draw this carbon has a stronger carbocation character. So bromonium ion is positively charged. But if you will, I can actually redraw it. That would not be a correct representation for it. But to some extent, I can draw it this way. Of course, this is not happening because if this is not true, because in this case, incoming nucleophile can attack this empty p orbital from both sides. So there is a stronger carbocation character. So if you wish, bromide is further away from here than from here. This is secondary, this is tertiary. And that's why the incoming bromide will always attack at this tertiary position, even though it's more sterically heated. And again, you will see that with oxymercuration. Is that concept clear? You have bromonium ion, you have three members ring. Okay? I'm going to draw it out. If there is a substituent here, we write the positive charge on bromine, but in fact, there is a positive charge spread all over this ring, and this carbocation has a large delta positive. Because it's tertiary, again, it's more stabilized. That's why the incoming bromide will always attack this particular carbon. Is that clear? That will always be the case. Whenever you have a more substituted double bond, you have X or anything positively charged, the nucleophile will attack from an opposite phase more stabilized carbocation. Okay? Or should I say, carbon with more carbocation character.
Can you explain why it's slightly positive again?
Because it's stabilized. If you wish, you can think about it that the length of the bond is kind of longer. It's stabilized carbocation, just like the stability of the carbocations. Stability, the tertiary is more stable than secondary. This bromonium, it's positively charged. The bromine is positively charged right here. But, so they all bear a certain extent of positive charge. And this one has more because it's capable to stabilize more. Okay? Is that concept clear? Okay, so once again, reaction with bromine, form our bromonium ion. We can do it either from the top, from the bottom. Incoming nucleophile, which is bromide, will attack opposite to the bromonium ion into more stabilized carbon, shouldn't be carbocation. It attacks carbon with more carbocation pair, which is always more substituted carbon. And again, you can envisage that. You can think of that as just double bond and methyl. So this one will have no substituent. This one will only have one. exactly the same thing will happen. This is more stabilized, more substituted carbon. So this is the mechanism for us. And I think we'll discuss that a fair amount of time. Yeah, so you see that's what I was talking about. The net positive charge is available at both carbons. It's not just bromine that is positively charged. The charge is spread. It's just the one that is more substituted bears more carbocation pair. That's why the substitution occurs at this particular carbon. Okay, let's take a look at the reaction with, again, alkenes with bromine in the presence of water. So I'd like to remind you that previous reaction was done in ether. Okay? That's why salt is very important, because ether is just non-reactive entity. It's there to solubilize the starting material. Okay? So they can move through and react. Now, this is the outcome of the reaction of alkene with bromine in the presence of water. So what happens first? We know that already. Whenever you see alkene and bromine, it's going to be bromonium ion. The same chloronium ion. So, bromonium ion is formed. There is a potential for bromide to attack our bromonium ion. Forget about this. Let's say they're equally substituted, therefore they will bear similar amount of positive charge. So who wins? Bromide or water? I mean, I think it's pretty obvious that water will win. And the reason for that is, if you put water, let's say you put one equivalent of alkene and one equivalent of bromine, and then you use water as a solvent, the concentration of water is simply much greater than that of bromide. Is that clear? So this is just we add water in much larger amount. That's it. And that's what we have. Now, water is competing with bromide as far as nucleophilic substitution, and it wins just because there are a lot of water and very little of bromide. Okay, so this is pretty much the same concept. I think we've discussed that a fair amount of times by now, but let's say that again. Same bond. It's the same story with water as with bromide. They open first bromonium ion, and then water will attack the carbocation with the most, so the carbon with the most carbocation ion. Just like our bromide did. The only thing that you do, you have to put your chlorine, bromine, iodine, and add water to the reaction mixture. Okay? And that's how you form halohydrate. You don't put water. If you don't specify, I would assume that the dihalite will form. Again, another very important point. When you write the reaction mechanism, make sure you include all the charges. You include the relevant. You don't have to draw all electron pairs for all atoms on the page. That's but at least you have to include the electron pairs of the relevant of the nucleophile. You have to include the charges. Sigma bond goes to bromine atom. Positively charged water comes in. Another water picks up the proton. So in this case, actually, you should draw a lone pair. Okay? Whenever you have an attack or a living group, make sure you draw the relevant lone pair of electrons. Keep an eye on the charges. There's a conservation of charges. Always the sum of charges from one side of the reaction should be equal to the sum of charges on another side. So just again, like with the reaction with bromine, it's anti-addition. You can form